Hi, this is Math Kimchi, and today we will learn about recursion. And I'm not talking about recursion in shapes, I'm talking about recursion in programming. And it's when recursion occurs when a function is defined by itself. So a recursive function defines itself, or calls itself. And there are two parts to a recursive function. The first one is the base case, when the solution can be found without recursion, and the recursive case, which is when you solve the problem by solving a simpler version of the problem, and that simpler version of the problem is solved by solving an even simpler version of the problem, and it gets simplified until it becomes the base case. It's so simple that it's the base case, and we know how to solve it with our recursion if it is the base case. And oops, I have prepared a function that finds the factorial of a number using recursion. So the base case is when we have to find 0 factorial, and we'll actually say that it is 1, because the reason why 0 factorial is 1 is because 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, and 4 factorial is 24. Well, it's hard to find a particular pattern right now, but actually we can see that 1 times 2 is 2, and 2 times 3 is 6, and 6 times 4 is 24, and therefore 0 factorial times 1 should be 1, and that means that 0 factorial is equal to 1. Anyways, I did get a little off track, but after we return 1, we actually don't need an else, because when we return something, everything below the return is ignored in the function. And if we are not asked to find the factorial of 0, we want to get to a place where we can use the fact that 0 factorial is 1. And we do that by saying, and this is the recursive case, the factorial of n minus, or the n factorial is equal to n minus 1 factorial times n. And it is pretty simple to see why that is. And I wrote it down here. And we see that to find the factorial of n minus 1, we're actually using this function. So in this case, the function has itself in it. It is defined by itself. And in this one, we are using a loop instead of recursion. Here we are not defining factorial, not recursion, by factorial, not recursion. It just uses a for loop, and so this is not a recursive function. Although it does work, and it is actually faster. And let's just run this. So if you do like factorial 0, you get 1, and factorial 10, that. And that is 10 factorial, and if we do nr factorial and 0, you get 1. Well, this one is pretty weird because it's even with like -1, it will say 1. So like recursion negative, I don't know, but yeah. And this does not happen with recursion, and I will explain more on that later. But one thing I also wanted to point out is that we can't find the factorial of anything above 1020 or something like that. So if we go like 1030 factorial, we will get an error sign saying that we have used recursion too much. And that can be fixed by sys.set recursion by using this. Okay, I'll just do that. So now we can do factorial 030, and doing this does not impact loops, I think. And so now I will get into why we have a maximum recursion depth thing. Although it might seem pretty useless, the reason why we have it is because, well, yes, we still have a recursion limit. It's just super big. And if we do factorial of -1, oh wait, actually I'll just get rid of this sentence. But factorial, well, what happened here was that the computer could not calculate something this big, and so it just decided to quit. So if we do this, we'll get a maximum recursion depth error. And it is useful because if it did not stop the program, well, first of all, it would have restarted the shell or restarted Python, and I would have to run it again. And also, if Python did not restart, I would have had to force quit the program or just let it run forever, since we want to get num to 0, but we are subtracting 1 from -1, but we want to make -1 bigger because 0 is bigger than -1, but all we are doing is making it smaller, and so we will never actually get to factorial of 0, and so we will just have to let the program run forever if there were no limits. And another time that this does it, when it's not necessarily a negative number, is when we do any kind of non-integer. This is because we want to get num to 0, which is an integer, but we will always be stuck at like a decimal number or a non-integer number. And now that we have gotten a basic idea of how to use recursion, I will give you one challenge to try to solve. And this is one of my favorite challenges with recursion, and it should be pretty simple, but it is with the Towers of Hanoi, and the rules are at the start there are n number of disks on peg number 1, and there are exactly 3 pegs, and each disk should be smaller than the one below it, so it progressively gets smaller as you go up. And you can only move one disk at a time, and at no time can there be a small disk below a bigger disk. And the goal of the program is to move all 3 disks, or all n disks, to peg number 3 while following the rules. And my hint to you is that you can move everything to peg 3, or my hint is that you first move the top n minus 1 disks to peg number 2. So everything but the very bottom disk should go to peg number 2. Then you make the very bottom disk go to peg number 3, or the nth or the biggest disk. And then we move all the n minus 1 disks from earlier to peg number 3. And we move n minus 1 disks from peg number 1 to peg number 2, and later peg number 2 to peg number 3 by a similar way that we moved n disks to so we do that by using a similar method as how we moved n disks to peg number 3. So it's basically just recursion. So we're just replacing like n minus 1 with n and changing all the peg numbers. And that is all I have to say for this video, and thanks for watching.